All right, hello and welcome back to another video for Math 5 Pre-Calculus. Today we're going to cover a couple of topics on in this video, and we'll cover them very briefly. But the two topics that we're covering are function composition and inverse functions. And if you're working on worksheet number 3, this corresponds to problem number 8. 8 talks about function compositions. Problem number 9 talks about inverse functions. And problem number 10 also talks about inverse functions. And in a sense, actually, problem number 8 also talks about function composition because, let me see. 9 and 10 cover inverse functions, but 9 and 10 also require function composition in order to check that the functions that we're given are inverse functions. So, okay, so the main problems we're focusing on is 8, 9, and 10. And there is another problem. Problem number 1 is also on function composition. Maybe we'll talk about this one as well if there's time. Okay, so this is not intended to be a very long video, just a quick review of these topics. Okay, so if we read problem number 8 in our let's see. If we read problem number 8 in our worksheet, it says, given a function f of x and g of x, find the compositions and identify the domain for each new function using interval notation. Okay, so here's a problem from the textbook from section 2.8. And we are going to find the compositions f of g of x and g of f of x. Okay, so before I do that, I do want to talk about the domain of each of these functions, though. The domain of the function f, if you remember how to find the domain of a radical function, you take the inside, set it greater than or equal to 0, solve for x, so x is greater than or equal to 3, and so that tells us the domain is all numbers from 3 to infinity. And then the domain of g, which I'll use d of g here to indicate domain of g. The function g is just a line. It exists from left to right, everywhere. So its domain is all real numbers. Okay, so we are asked to find, in problem number 8, f of g. And of course, I'm using different functions because I've chosen mine from the textbook. Oh, actually, they're very similar. They're very similar, but a little bit simpler, actually, than what's on the worksheet. F of g, fog, sometimes this is called, fog of x, or f of g of x. The way that this is defined is just the function f, and you plug in g, the function g into f. Okay, so if we talk about what the function f is, the function f is the square root of the input minus 3. But we're not going to put x here since it's not f of x that we're dealing with now, but it's f of g of x. So we're going to plug in g of x into f. And so our new function is the square root of 3x plus 1. Okay, there is our composition function, the square root of 3x plus 1. That's not too hard to find. Now let's go ahead and find its domain. And I strongly recommend that you find the domain before you make any simplifications to the composite function. So notice here is where we first encounter our composition of functions, where we plugged in g into f. And so we can try to find the domain of this function here. I'll do it on the side here since I didn't give myself too much room. But the composite function is a square root function. And under the square root, we have 3x plus 4 minus 3. And we want to set that greater than or equal to 0. All right, so 3x plus 1 is greater than or equal to 0. If we subtract the 1 over, 3x is greater than or equal to negative 1. And dividing by 3 on both sides gives us x is greater than or equal to negative 1 over 3. And that gives us the numbers from -1/3 to infinity. Okay. There is the domain of my composite function. And I could graph this. Maybe we'll graph it afterwards. To see the function. And we'll see that that is its domain. So let's take a look at the other composite function. If we take a look here, we should be able to also find g of f of x. And f of g and g of f, notice the circle there does not mean multiplication. It means, composition of two functions. The order of composition does matter. This is going to be the function g with f of x plugged into it. And so g is the function that takes 3 times the input and adds 4. And so the input into the function g is the function f. The function f is the square root of x minus 3. All right, so we can try to simplify this, but no, it doesn't really simplify. There is nothing that we can simplify, so I'll just write it one more time without the parentheses. 3 times the square root of x minus 3 minus 4. And if I wanted to find the domain of this thing, I would find the domain, as I mentioned before, when we first combine the two functions using composition, I can find the domain of that function, and that will be the domain of the composition. Okay, and we can see, well, that function is a radical function. It's going to be found in exactly the same way as we did for f. X minus 3 must be larger than or equal to 0. And so x must be larger than or equal to 3, which means the domain is all numbers from 3 to infinity. All right, so notice one of the times the domain of the composite function came out to the same as the domain of one of the previous functions. Okay, that doesn't always happen. As you can see here, the domain of the first composition that we did was not equal to the domain of either one of the two functions by themselves. Okay. And you might be asking, you might have thought maybe when we were doing this problem here with the f of g, why didn't I just take this 3x plus 1 and use this function here to find the domain, and set it greater than or equal to 0? And there are cases, as you'll find when you do problem number 8, where things might cancel out when you do some simplification to your composite function. Things might cancel out that may kind of hide what the domain is. So when you're doing these problems, if you'd like, one good little tip is to, you can also graph these functions, graph each of them on Desmos. And when you're doing problem number 8, you'll notice that they're not going to be completely identical. So to find the domain of a composite function, the most accurate way to do it would be to find the domain of the composite function when you first compose the two functions, when you first plug one into the other, before any simplification has been done. All right, so there's how you can find a composite function, f of g or g of f, and then how to find its domain. Okay, so problem number 9 then says, for each pair of functions below, find f of g and g of f, and use your results to determine whether f and g are inverses of each other. Okay, so let's go ahead and take a look at these two functions from problem number 61 in section 4.1 of our textbook. So to determine whether two functions are inverses of each other, we just need to do function composition. It turns out that if you compose a function f with its inverse, which has the notation f with a little -1 as a superscript. If you compose two functions and they are inverses of each other, then the result is going to be just x. Nothing else, just x. And if you compose the functions in the other direction, find f inverse of f of x, then if these two functions are inverses, the result is going to be, again, just x. All right. So let's go ahead and compose these two functions and see if they are inverses of each other. Sometimes you can kind of tell whether two functions are going to be inverses of each other just by looking at them. F is a function that squares a number and then subtracts 3. And g is a function that takes a number, adds 3 to it, and then takes the square root. So it seems a little bit opposite. F and g seem to be opposites of each other, or inverses of each other. They seem to undo what the other one does. So let's go ahead and check. Let's find f of g of x. And this is f of g of x. So I'm going to take my function f, which is x squared minus 3. But into the x, I'm going to plug in g, which is the square root of x plus 3. All right, so we simplify this. The square root, when it's squared, the square root and the square can go and cancel each other. And so we get x plus 3 minus 3. And you can see that plus 3 and the minus 3 are going to cancel. So we get x. Hey, that seems to indicate that f and g are inverses of each other. Now let's check the composition in the other direction. G of f of x. That's the function g with f of x plugged into it. So the function g is the square root of the input plus 3. The input here is f of x, which is x squared minus 3. And if I simplify here, the 3's cancel, and I get the square root of x squared. And the square root of x squared, I get x. All right, so we did the composition in both directions and got x both times. So that tells us that these two functions are inverses of each other. Okay, I do want to give an example just really quickly of two functions that are not inverse of each other, what their compositions would look like. So let's just get let's just throw in another function here. And the other function that I'm going to define is just going to be h of x is equal to, let's say, the square root of x minus 3. And now my question is, are f and h inverses of each other? Well, if they are inverses of each other, then their composition, f of h of x, should give me just x. So let me go ahead and try to find f of h of x. That's going to be my function f with h of x plugged into it. My function f is the squaring function minus 3. And I'm going to plug in h. That's the square root of x minus 3. The square root and the square will cancel again, and we get x minus 3, which gives me x minus 6. Because I didn't get just x, I got a minus 6 with it, then f and h are not inverses of each other. That's already enough to say that the functions are not inverses of each other. I can even compose them in the other direction, even though I don't need to. I do have enough information now to say that they are not inverses of each other. But let's take a look at the other composition. H, which is the square root of the input minus 3, and the input is the function f, so that's x squared minus 3. And notice this becomes the square root of x squared minus 6. And I can't simplify that any further. So I can conclude that H and F are not inverses of each other. Since, this expression was not equal to X. Okay. In fact, there is, I forget if this is in the book. It's been a while since I've read it, but f of x will only have one inverse. It has a unique inverse. And we actually just showed in green that g of x was the inverse of f. So, it was just an exercise to see if h was also an inverse of f. But if you know that there's a unique inverse, then h, we can say h will definitely not be an inverse of f because f only has one inverse, and it was the function s squared of x plus 3. All right, but we've proven it here. If you get anything other than x, like an x minus 6 or anything other than x, then the two functions that you composed are not inverses. All right. Well, suppose you're given a function. Now we're moving on to problem number 10 in the problem number 10 in our worksheet. And it says, for each function f below, find f inverse, the inverse function of f, then find the domain of f inverse and write it using interval notation. Okay, nice. So here we're given a function, and you know what? Let me go ahead and actually change this. I'm going to change this slightly and just make this, so this is no longer problem number 42 in our textbook. I just changed it a little bit, but this one works out pretty well. We can actually do both if anybody is interested to see the other one as well. So I'll write f of x down here. Or let me write g of x actually. So here's number 42 in section 4.1. G of x equals the cube root of x plus 3. And I'll show why I made this change. It's just so we can see something in this problem here. It makes it a little bit clearer with the square root rather than the cube root. All right, so the square root of x plus 3, we actually should be able to graph this really accurately because we've already talked about function transformations in this class. And so I'll graph it here. It's going to be just 1, 2, 3, 4, 1, 2, 1, 2. So it's the square root function shifted 1, 2, 3 units to the left. And so the graph looks something like this. There we go. And it turns out actually that the inverse of a function, let's say that this is the function f, and I should have graphed it in blue, but there you go. The inverse of f is going to be symmetric about the line y equals x, this red line that I've just drawn. So actually one way to find the inverse is by just using the graph and using symmetry and reflecting each of the points about the line y equals x, making mirror images of them about this line y equals x. So here is the inverse function of f, and I'm going to call it, oh, and actually I could have gone a little further with that. I'll call it f inverse. Okay, so what does that look like? That kind of looks like a parabola. And yeah, I think it's not too much of a stretch to say the inverse of a square root function is going to be a square function or parabola. Now there's only half of a parabola there. So let's go ahead and take a look at the domain of f. We did one earlier. So, and actually we can tell from the graph here that the domain is -3 to positive infinity. And I'll also write the range of f. The range of f, we can see from the graph, is just the y values, which start as low as 0, up, increasing to positive infinity. Okay, we'll see the point of finding the domain and range of f in just a moment. So, problem number 10 asks us to find the inverse, f inverse. Okay, so there are a few steps, just a couple of steps to do this. So let me go ahead and write my function again. So here we'll start the problem. F of x equals the square root of x plus 3. The first step is to let y take the place of f of x. Then to switch the places of x and y. That was step 2. Step 3 is to solve for y, which this here is, just depends on the function. Here is a square root, so we'll square both sides. And we get x squared equals y plus 3. And then subtract 3 on both sides. Gives us x squared minus 3 equals y. Or y equals x squared minus 3. Once you've solved for y, this is now the inverse function. So the last step is to replace y again, or get rid of y, and in its place, we don't put f of x, because this is not the original function anymore. We put f inverse of x. That little -1, it looks like it's an exponent, but it's not an exponent. It's just a notation to say that this is the inverse of the function f. Okay, and so the inverse of f is x squared minus 3. And this looks like a parabola. This looks like the equation for a parabola. And it is. The only catch here is that it is not the entire parabola. It turns out that the domain of an inverse function is going to be equal to the range of the original function. And so the range of the original function we found was 0 to infinity. So the domain of f inverse is going to be starting at 0, an x value of 0, and going to positive infinity. And you can see exactly that happening. It starts at 0 and it goes, to the right and up, right? So the values of x start at 0 and go to the right. And, to the right. The function goes up as well, but for the domain, we only care about the horizontal travel. All right, so one nice property is that the domain of an inverse function is equal to the range of the original function. And it's also true if we wanted to find the range, which we're not asked for in this problem, but we'll just do it anyways. What's the range of the inverse function? Well, it turns out that it's just equal to the domain of the original function f. So if we go and look at the domain of f, that is -3 to infinity. So the range of f inverse, the y values that the inverse function will take on, will be starting as low as -3 to positive infinity. Notice it goes in the upward direction. Cool. All right, so that's how we do problem number 10. There are 4 steps essentially. We let f of x become y. We switch y and x. Then we solve for y, get y by itself. And the last step, once we've got y by itself, we essentially have the inverse function, so we give it the inverse function notation. And to find the domain of the inverse function, one way to do it is just to look at the range of the original function f. All right. And a lot of times students will ask, so I'll just answer it here. Where is the other half of this parabola? Right? Why don't we have the other half? And essentially, one way to see this is if you had both halves of this parabola, then when you invert it or reflect it about the line y equals x, then notice you would get this other half of a square root function, a lower half of a square root function, and that would fail to be a function because it would not pass the vertical line test. So we can, the inverse is only going to be half of the parabola in order for the inverse to be a function. All right, so there is also more details in the textbook. And yeah, I can just briefly give the details here, but essentially, if we had the whole parabola as well, this would not be, the entire parabola is not a function that can be inverted because it fails what's called the horizontal line test. Right? Remember, there was a vertical line test to test whether something was a function. There is a horizontal line test that tests whether or not a function is invertible or has an inverse. And uh, if a horizontal line crosses more than once, then it is not invertible. It does not have an inverse. And because of that, we restrict the domain of the parabola to only include half of the parabola. That way it will now be invertible. All right, so there is a lot of detail there. And I'm not going to go into all of the detail here in this hopefully short video. But it is, talked about in our textbook. So you'll want to talk about that or read that. Notice here, horizontal line test. If every horizontal line intersects the graph at most once, the function is one-to-one and therefore invertible. So this linear function here is invertible. This one is not. Okay, so there are some exercises there, identifying one-to-one functions. You can read through there. And then why do we care about one-to-one functions? We care because one-to-one functions are invertible. You can find an inverse of them. And so here is the parabola example that we were talking about, or a similar one. The entire parabola is not invertible, but if you just only include half of the parabola where x is larger than or equal to 4, let's say, then that function is one-to-one. This solid part here is one-to-one, and we can find an inverse for it. All right, here's something else that we talked about. The composition of two inverse functions. If the functions are inverses, then the composition just comes out to x. All right. The steps for finding an inverse that I gave are also right there. You can take a screenshot of that or write that down. Cool. Yeah, so there's a lot of information here. Very good information. All right. So let's go ahead and go to our last problem and we'll be done with this video. Okay, I have it written down. The last problem is similar here. It's just a cubic function. And the reason I didn't want to do this one first is, or sorry, not a cubic function, but its inverse, the cube root function. The cube root function, we can also graph. We might not know what this one looks like exactly, but it looks like this. 1, 2, 3. 3 units, shifted to the left. I'll just do a sketch of the function. It looks like this. Okay. So it is one-to-one. It can be inverted. And so let's go ahead and see how we would do that. We're going to go through those steps that we saw in the textbook that we gave earlier. We let y take the place of f of x or g of x, the function notation. We switch x and y, the places swap, so y becomes an x, the x becomes a y, and then we solve for y. In this case, a cube root can be eliminated using a cube. So x cubed is equal to y plus 3. If we subtract 3 from both sides, then we get x cubed minus 3 equals y, or y equals x cubed minus 3. And then the last step is to use the inverse function notation, and we're done. We have our inverse function. We do want the domain of our inverse function. So the domain of the inverse function, this is a cubic function. We could find its domain just directly for this case, but let's go ahead and just use the range of the original function g. We have the graph of it right here. You can see that the function goes down and to the left, and then up and to the right. It looks, like it's not increasing very quickly, but it does continue to increase, as it goes further and further to the right. So the domain of G inverse is the range of G, which is negative infinity to positive infinity. Oh. All right. And if we inverted this, let's see here. The x cubed, the function G inverse, x cubed minus 3, well, that's 1, 2, 3 units shifted vertically down, and it would look something like this. These are just sketches, of course. We could use desmos.com to graph these, and they'd look, very, very accurate. All right, we can see there that the domain of this inverse function, yeah, I guess it's believable to think, continues to go to the left, and it continues to go to the right, negative infinity to positive infinity. All right. Very good. Yeah, let's go ahead and answer a couple of these questions, maybe on problem number 1. Let's see if we can answer a couple of these. Okay. Decide whether each statement below is true or false. Give an explanation for your answer. Recall that we can write f of g of x as f of g of x. Okay. Yeah, so let's start with part C. In general, f of g is the same as g of f. Is that true in general? Well, here we have an example of, f of h, where we got x minus 6, and h of f, where we got something different, the square root of x squared minus 6. So no, in general, the order of composition does matter. They will not be equal, usually. Oh, and then we have a similar question here. In part D, the composition f of g is never the same as g of f. Is that true? No, that's also false, because sometimes the composition is the same, as in this case here. If they're inverses, then the composition in both directions is the same. It's just x. Okay, so yeah, I would say false for that one as well. Now we can take a look at A. Maybe I won't do the whole thing, but it says f of x is equal to x squared plus 2. So or if f of x is that, then f of 1 is equal to 11. Well, one way to do this would be to find f of x, the function f of x, and then plug in 1 and see if your output is 11. Okay. Yeah, I'll do it this way. There is a shorter way to do this problem, but I'll show this way just because it's asking is f of 1 equal to 11? With what we've learned so far is, well, we can find f of x and then just plug in 1 and see if our output is 11. So f of f is just going to be f with f plugged into it. Okay, so f is the function that takes something, it squares it and adds 2, and we're going to plug into that f. Okay, this is not that fun. X squared plus 2 times x squared plus 2 plus 2. If I do a little bit of foiling here, x squared times x squared is x to the 4th. X squared times 2 is 2x squared. X squared times 2 is 2x squared again. And 2 times 2 is 4. And there is a 2 there. So we have f of x. It is x to the 4th plus 4x squared plus 6. So now we can use this function to find f of 1. We plug in 1. And we do get 11. Okay, so that's true. There is a shorter way to do this. I'll give you a hint. f of 1 is equivalent to that other f of 1. So if you can find f of 1, as I've written it there, in pieces, you can find, answer this question a little bit quicker. All right. And I will let you think about the next one. But f of x, now I'm kind of curious. F of x equals x squared for part B. And the square root of x minus 3. Let's see here now. Now I'm curious. F of x equals x squared, and g of x equals the square root of x. I don't know, is it plus 3? Minus 3. Like that. Okay, so zoom in a little bit. X minus 3. So what's the domain of the composition f of g of x? Oops, is it x plus 3 or x minus 3? X minus 3. Let's change that to a minus. Okay. So what is the domain of the composition? That's the question. So let's find the composition just by using f of g of x. The domain seems to be 3 to infinity. So yeah, take a look at the question. The question says if f of x is x squared, g of x is equal to the square root of x minus 3. F of g of x, it's asking a question about the domain of this function. F of g of x is f, the squaring function, with g of x plugged into it. And if I simplify, the square and the square root will cancel, and I get x minus 3. My composite function is equal to x minus 3. So what's the domain of this function? Is it negative infinity to positive infinity? That's what the claim is in part B. Or is it something else, like 3 to infinity? And so if you think it's negative infinity to positive infinity, you mark true. If you think it's something else, you mark false. And then we want to give a little explanation for why uh, the domain is either negative infinity to positive infinity or something else. Okay, so big hint there. All right. That is it for this video. I just wanted to make a quick video just to kind of summarize the topics here so that we can, if we don't get it all in class, we can come back to the video and watch a couple more examples. I'm sure there are many more videos available if you just Google or go on YouTube and look up function composition, inverse functions, or things like of that nature. You can find many more examples and much more detail there. All right, so yeah, don't forget to like the video and comment or subscribe. Yeah, let me know what you think.